So now that we've emphasized how important state variables are, let's do another extremely important calculation. We want to calculate the change in internal energy of the system for two very important trajectories: the isochoric trajectory, where volume is unchanging, and the isobaric trajectory, where pressure is not changing. So just as we always do in doing a calculation, we always write down the first law of thermodynamics because it clarifies our thinking on any problem. So now let's calculate the change in internal energy along path 1. This is our isochoric pathway. We're going to call that delta U along path 1. Now we come to a very important transition because we have calculated prior to this that the heat going into a solid or a liquid is some proportionality C times the change in that temperature. And this is the heat capacity of that particular body or that vessel with the liquid in it. And we've done this many times with the Joule experiment. But now we have a compressible gas. We have a gas for which the pressure times the volume is equal to the number of moles times the gas constant times the temperature. So if it's compressible, it makes a big difference when we calculate the change in internal energy along a path of constant volume versus one of constant pressure. So let's write the change in internal energy along path 1. That change in internal energy is equal to the number of moles times a quantity which we call the molar specific heat at constant volume. So I have to indicate that with a sub V, a subscript, because it's very important to keep that differentiated. And then I multiply that by the change in temperature, which is the final temperature minus the initial temperature. All right. Well, now let's do the same calculation along path 2. Now along path 2, I have a contribution from the heat. I'm going to write this as Q plus W. But this is going to be the Q as well as work done along a path of constant pressure. So in this case, I have the number of moles times molar specific heat at constant pressure times final temperature minus initial temperature. But then I have one other term, minus the pressure times the change in volume. Well, I know that PV equals nRT, so I can express this in terms of the temperature change, which will give me nC sub P times final temperature minus initial temperature minus P delta V. Well, that's going to be equal to minus nR times final temperature minus initial temperature. So that's very important. The relationship between those is very important. The first thing to point out is that delta U along path 1 is equal to the minimum energy to get from T initial to T final. That says something extremely important. It says that any time I want to calculate the change in internal energy of the system going from one temperature to another, I can always do this by solving exactly the same calculation, the number of moles times the molar specific heat at constant volume times the temperature difference between those 2 points on a pressure volume coordinate system. But there's something else that's extremely important, and that is that U is a state variable, and that means if I move from the initial temperature to a final temperature, it doesn't matter what path I take, whether it's isochoric or isobaric, the change in internal energy along each pathway has to be the same because it's a state variable. I've gone from an initial to a final condition. And that means that I can equate the expression along path 1 for the change in internal energy to that along path 2. And that gives me nC sub V T final minus T initial. That's the change in internal energy along path 1. but that's equal to the change in internal energy along path 2, NC sub P times final temperature minus initial temperature minus NR times temperature final minus temperature initial. Well, look at that expression. We can cancel all sorts of things. The number of moles cancels out. The difference between final and initial temperature cancels out. And we have the expression that the molar specific heat at constant volume is equal to the molar specific heat at constant pressure minus the gas constant. That is a profoundly important conclusion. And we can glance over and look at our molar specific heats of different gases. Let's take monatomic gases. Let's take atoms, helium, neon, argon. The molar specific heat at constant pressure is the same for each of those. The molar specific heat at constant volume is the same, and the difference is exactly equal to our gas constant R. If I take diatomic gases, then the molar specific heat at constant pressure is larger than it is for an atom, and the reason for that is that molecules vibrate and rotate so they can take up more energy. The molar specific heat at constant volume is smaller than that at constant pressure, but the difference is also equal to the gas constant. And so it's very important to realize that when we're looking at these molar specific heats at constant pressure and volume, the molar specific heat at constant pressure is larger than the molar specific heat at constant volume. But it's the relationship to the gas constant R that's the most important.